Namaste to everyone. I am Dhruva Khadka from National Institute for Material Science, Japan. In this talk, I am going to present about the effect of rubidium incorporation in tin halide-based perovskite solar cell. Halide-based perovskite solar cell has some scientific issue, and the one is material instability, another is degradation phenomena, and it contains lead, and which is toxic. And device physics of this material or this device based on halide-based perovskite are still being explored, and there is much things to be known. And it has toxic lead, so it has a toxicity issue. And if we see the lead halide based perovskite solar cell, we have already obtained device efficiency more than 25%. And if we compare this with cadmium telluride solar cell, which already have nice efficiency more than 21%. This in cadmium telluride solar cell, cadmium is being recycled, and due to the toxicity of cadmium. And if we compare property of lead and cadmium element, cadmium is less soluble than lead, so being more solubility properties, lead is more dangerous than cadmium, so we have to worry about its application. And we have to, if we want to commercialize it, we have to think about replacement of lead in lead halide perovskite solar cell. So there are some candidate tin based perovskites, bismuth, or other types of solar cell material. And this lead and tin based perovskite solar cell, if we talk about the lead and tin, lead is toxic but stable. Tin is non-toxic but it is unstable, and it has SN2 plus state, and which can have oxidation, and there is big oxidation issue of this material. And a good point for tin based perovskite solar cell is its band gap is lower than lead based perovskite solar cell, and this band gap lies within the range of optimal band gap of theoretical calculation. And then if we could optimize tin based perovskite solar cell, we can have much higher efficiency than lead based perovskite solar cell. There are many work on tin-based perovskite solar cell, and single cation and mixed cation, and there is some structure of 2D and 3D, and it is being increased by tailoring morphology, defect passivation, and with additive. And recently, professor from Japan, Professor Hayase, he got if a device efficiency with tin-based halide perovskite more than 13%. This is very promising, and there it shows the future and competitive this characteristic to the lead halide based perovskite solar cell. And if we see the effect of additive on halide based perovskite solar cell, this one is cubic structure, and if we of lead halide perovskite solar cell, and if we consider add this cesium on this structure, and it has different effect on lead based perovskite and tin based perovskite. In case of tin based perovskite, we can see lattice contraction, but in case of lead based perovskite, we can see octahedral tilting, and this has these lattice construction and octahedral tilting has different effect. In case of tin, it induce lower band gap, but in case of lead based perovskite, it induce wider band gap. And it is reported by McGehee group, and they found that there is increasing and decreasing trend of band gap energy. And one good point is it has structural regulation with cesium additive, that is some additive acid tailoring, and for late tin based perovskite, it has structural stability, and which is good for stability of tin itself, from oxidation and from other aspects as well. And this is the schematic of device fabrication. Here is precursor stoichiometry. We varied rubidium content in ferromedium tin halide precursor, and this is the device with the rubidium incorporation, and this one is device pristine one, and we can see the difference. And this shows the XRD pattern, effect of rubidium on XRD pattern, and we can see the XRD shifting, XRD dominant peak shifting. This indicates the incorporation of rubidium in crystal lattice of ferromedium tin halide, tin iodide film. And it also has effect on morphology. So we can see the compact film and better coverage film, and this is PL spectra. And with the rubidium incorporation, we can notice rare shifting, and this is also reported by other group, and they are but different with different that is cesium tailoring, and in case of cesium, they also report rate shifting of band gap energy. This is the device structure, and this one is device performance, and we improve the device efficiency and from 3.22 to more than 5.89, that is close to 6, and that's it means we improve the device efficiency with the structural regulation. And we are to confirm the role of rubidium. We also tune the material property using the rubidium halide derivative and ferromedium halide derivative, and this result confirm that rubidium has key role in enhancement of device parameter. And it also has beneficial aspect for the suppression of oxidation. We can see here for the pristine one, SN4 plus content has been reduced to less than to close to 8% with the rubidium additive film. And to understand the device physics and we use the capacitance spectroscopy, and this is the capacitance frequency response, and this one shows the capacitance at different temperature. We can see here some difference at lower frequency range, but if we compare here capacitance varied with temperature, we can see faster decreasing trend or faster changing trend of capacitance with temperature for the pristine one, and slower changing trend of capacitance for the rubidium incorporated device. This indicates that the capacitance response, slower capacitance response, indicates the less defect to be freeze out with decreasing or with change in temperature. This means if our material or our device has higher defect, it must have faster response with different temperature, but if we have the lower less defect, it has slower defect, slower decreasing or increasing trend, or slower changing trend with temperature. With considering the capacitance variation at different temperature, we estimate the RNS plot, and for the pristine one we found the deeper defect, but for the device with the rubidium incorporation, the defect has been shallowed, that is this shallower defect close to 0.41, you can see here, and it has the defect has been passivated or has been shallowed. And this is the calculation of trap profile, and we can see the suppression of defect, mitigation of defect profile with a rubidium incorporation, and this also support our device performance, because we can see the noticeable improvement in VOC, and that is correlated to the defect control or defect activities as well. And we also study the device stability. This shows the device performance, normalized device performance. We can clearly see here better stability with rubidium incorporation, and these are the front and back side of the edge device. We can see noticeable difference in pristine one and rubidium incorporated one. Rubidium incorporated one shows the pretty similar color, but it has we can see the color change. Along with that, we also study the film stability by oxidative pattern, and we can see here after for the pristine one, after 15 days, we can see the thin iodide peak here. But in case of rubidium incorporated film, there is no such a distinct peak for thin iodide. This means this film, that is rubidium incorporated film, is more stable, and that is good news for us. And with the this report, that is structural regulation with the rubidium incorporation, we have a little bit, we have improved results. So following that, we also use this approach for the 2D and 3D, and we have uh, improvement in device performance. We got more than 8% device performance with 2D, 3D, and structural regulation for the thin halide based perovskite solar cell. This is the sum of my talk. And from the rubidium incorporation approach, we can get uniform morphology and better crystallinity, and we also suppress the oxidation of SN2 plus, and our the SN with the suppression of SN2 plus, there is also mitigation of recombination phenomena. Of course, we have improved device performance from nearly 3% to 6%, and this is the figure. It shows the improvement in device performance, and that is correlated to the suppression of defect profile. And I would like to acknowledge for the grant to the Hitachi Global Foundation for the Kurata grant and ISOS fellowship. And I will also like to extend my gratitude to our PI group leader, Professor Kenjiro Miyano, and Dr. Yanagida, Dr. Shirai, me, of course, and our team. And I like to have question and answer. Thank you very much.